Welcome back, everybody. In the beginning of the lecture, I just wanted to give you some basic overview of the layout of what we will do today, and say something about the exercises this week, and also come with some other practicalities. So today, we're going to use most of the first lecture to wrap up the discussion about partial differential equations and ordinary differential equations, and how we can solve these with deep learning methods like neural networks. And the examples which you will see here, they are examples which give you a kind of guidance on how you could use your program for a neural network to solve a differential equation. And then we are going to compare with the cases where we have analytical solutions, obviously, but also with some standard numerical methods like Euler's method, which is actually not the most favored ones. But this gives you an example on the flexibility of neural networks. Now, when we are done with that, we are going to enter the discussion of classification problems of images. And that means convolutional neural networks. So that's going to be one of the topics which will keep us busy till the end of next week. And then we are going to move over to recurrent neural networks. And we will stay with deep learning methods till the end of the semester, which means that we will fill in information about so-called autoencoders. That means that you will have been exposed to 4 central deep learning methods, which then allow you to choose among these methods when you want to define your own data set for project number 3. So hopefully you will have enough flexibility and freedom to apply different methods and test out these on the data sets which you have. So typically, a path which many people have taken, if you have images, then they start with neural networks. And the problem with neural networks is that they represent so-called affine transformations, which means that we have dense matrices, which we multiply with dense matrices and dense vectors. Whereas when we now do a convolutional neural network, the kind of overarching view you can take is that this is a method which is used to reduce the dimensionality of the problem. And this is done by the mathematical process of convolution, which I will describe later today. In principle, this means that you apply a filter to your image. So think of you wanting to recognize whether this is a house or not. Then clearly you would not keep track of all the information if this is an image with, let's say, 200 times 200 pixels. You may perhaps just want to keep information about where the windows are, where the walls are, where the roof is, where the doors are, etc. You won't keep track of all the pixels which represent the color of the house, because hopefully this house has been pretty well maintained and it has a uniform color. So this is an example of a filter which you would apply in order to recognize houses. And many of these filters are actually particularly designed for a specific problem. We're coming back to many of the more popular data sets. This is one of the methods, CNNs, convolutional neural networks, which actually paved the way for the breakthrough of what we normally call the deep learning revolution around 2010. So we will focus mainly on that. And this course will then serve as a starting point in case you want to look at generative methods in advanced courses or advanced applications of these methods. Because even if you have many pre-trained data sets on images, and this is often what people do, the field of convolutional neural network has moved very fast, and people now have specially designed filters for specific applications. And that is an art by itself. Now, as you can see from the notes here, there are several videos if you want to look into it. But for convolutional neural network, I mean, the textbook by Goodfellow, chapter 9, together with 11 and 12, give you a lot of the, the overview of what these methods are about. And chapters 11 and 12 are very useful when it comes to practical implementations of deep learning methods. It contains a bag of tricks and hints on how to train your network, which will also be useful in connection with the project you're dealing with now. So the lab sessions this week is simply about work on project number 2 here. And we also thought that we want still to give people some flexibility with the weekly exercises in case you haven't completed them. So coming to the weekly exercises this week, this is a lookalike of what you had in week 39 when we asked you to set up the GitHub address, an overleaf document, the basics of the report, and we will try to give you feedback again. Then there is a list of questions here, which follows down here. You don't need to answer all of them, as we say here. You don't need to answer all the questions, but these questions are questions which we made, which you can find useful when you are discussing the results of project number 2. So in project number 2, you're asked to come with a critical evaluation of a deep learning method, like a neural network, compared with what you did in project 1. So there are lots of these kind of questions about what do the things we are doing mean. So hopefully, when you look at these questions, and as I said, you don't need to answer all of them, they are more meant in a way as to guide you in making the analysis for the report. Does that sound okay? Goody. So, yeah. Yeah. So I think I said this during the lab sessions. So the kind of idea we always have practiced is that you will get the feedback roughly 10 days before the deadline of project number 2, which means towards the end of this week. And then we are going to upload the feedback to project 1. So that should give you guys roughly 10 days to, let's say, correct things, if the things you, which you got criticism about in the abstract or whatever. I hope that sounds okay, with 10 days before the deadline roughly. That's the kind of thing we are aiming at, hopefully. Any more questions about practicalities? Okay, so let's go back to differential equations. And this is a topic which I find a beautiful application of neural networks. And it follows much from the universal approximation theorem, which simply says that you can approximate a continuous function with one hidden layer. It doesn't specify the number of nodes, but you can fit a continuous function to a given degree. Now, the basic recipe here is that you make an ansatz for your solution given by a neural network, plus the initial and boundary conditions. And there are many ways to make this. And I showed you some of the simpler ones. And I just wanted to repeat some of the basic things which we do when we are going to set up a neural network as a solver for differential equations. So you could actually easily take your program when you have set it up for a regression type of problem and replace the type of data you have with a differential equation solver. So let's take a look at the mathematics again. And let's switch back to the whiteboard. So the basic machinery is a very intuitive one in a certain sense. If you now look at the typical differential equation, and this is one of the cases which we looked at last time, and after that, we are going to look at some other types of equations, like a 2-point boundary value problem. And then we are going to wrap it up with a standard partial differential equation, like the diffusion equation. And I know that every year there is somebody who is interested in solving differential equations because it may be related to your master thesis topic, but it may also be related to you having a general interest in solving differential equations. And there are many people in parallel follow a course on numerical solution of differential equations. So that fits. Project 3 has a variant dealing with differential equations. So what we did then, we started with something pretty simple. So let me quickly remind you of that. So we had a dg of dt, and this is the standard exponential decay equation, where gamma then is assumed to be a parameter which is larger than 0. X lives between 0 and infinity. And we know that the solution if we define a quantity G0, this is given by the solution at t equals 0, and I wrote x here, it should be t. And then we get a solution which is g of t and is equal G0 multiplied with the exponential of minus gamma times t. And this gamma is normally called the decay rate in exponential decay. And you can quickly see that if you insert that solution into the differential equation, that is a solution to the differential equation. So when we are solving this with neural networks, what is pretty common to do then is to define a new function, which we would then define as a function of t, and in this case we have only g, and its derivative, g of t prime. And this function is nothing but us taking the difference between the left-hand side and the right-hand side of the differential equation. It seems that everybody has written it down. So this function, let's just repeat it here. This function of t, and then I just write it like g of g prime. This is actually given by dg of dt minus gamma of gt, and that is equal to 0. So we actually want to drive this equation to 0. That's essentially what we are doing now. And then we defined a cost function, which is given by the following. So in general, this function f can depend on higher order derivatives. In general, so let's just write it down. We have an f of t of g prime. This can have a dependence on the second derivative and up to a given derivative. So that depends on the type of differential equation which you have. And now I'm leaving these kind of derivatives a little bit unspecified because these could be partial derivatives as well. So this g of m could be a derivative with respect to another variable than t. So this is the general equation, and that means that t then would have to be augmented with other variables. So if you have a two-dimensional function like the diffusion equation, which is actually one dimension in space plus time, so we say 2 dimensions, but it's actually 1 plus 1, that would have x and t as variables. And then you would have the derivative with respect to t, with respect to x, and also the cross derivatives. And we are going to set up these equations a little bit later. Then what we are doing is to define a cost function where we now let this g go over to a g trial. So t for trial. And that t trial here, I should, just a moment, let me change letters a little bit. Let me use an uppercase T, and then we have T here. And this depends then on time, and it's given by some function h1 of t plus a function h2 of t here. And this will also depend on a neural network, which takes as input t and has some parameters theta. So this is a neural network. Network with parameters. And this function which we have here is a function where we are going to set in the boundary conditions and the initial conditions. So this could contain boundary plus initial conditions. Now, for the function which we have now, this exponential decay, what we could do then is to make an ansatz. And you know that there are many ways of making the ansatzes. Sometimes you are able to guide the ansatz by some kind of solution which can be a lookalike, or somebody gives you a numerical solver which gives you a good starting point for the solution. And then you could use that one as a starting point for defining that function plus a neural network. So when I'm applying these methods to solving quantum mechanical problems, what I often do is that I bake in symmetries of the solution. So it can be a solution which has to be antisymmetric under the interchange of two particles, which follows from, for those of you who've done quantum mechanics, this follows from the Pauli principle. There can be other types of symmetry which I would bake in this solution. So this ansatz, which you see here, this G of t, is something which is guided by your insight about the problem. Okay? So in our case, we could now simply say that since we know that the solution is, we know that the G of t of time here is given by this G0 times the exponential of minus gamma of t. We could now make a guess and simply say that this trial function, G of t, could now be given by a constant, and we know the initial condition. So when you guys are solving differential equations, the initial conditions are known quantities. We know the initial velocity, we know the initial position, and we also know the boundary conditions. I mean, you poor guys are confined to be in this room, and this is the boundary, right? But there is a possibility to escape. So you can always escape through the boundary conditions, right? So what we could make now is a function which goes like G0. We just make an ansatz, and then we could now have t times a neural network. So n stands for neural network, function of t, and the parameters theta. So in this way, we have actually baked in the initial conditions. And we know that when t is equal to 0, then this g of t of 0 should be equal to g0. So this simple form is a way to make an ansatz for how the solution is going to look like. Then we are going to let the neural network find the best way to represent the solution. So it sounds almost too good to be true. But actually, the universal approximation is a theorem which is working behind the curtains here. So what we are going to define then is a cost function. So the cost function as a function of the parameters theta is then simply going to be a sum over all the points which we have, I equal 0 up to n minus 1. And then what we are going to do is simply to set up this function which we defined, this f, which you are going to drive to 0. And in our case, this is f, the t, it's a function of g of t, and it's also a function of g of t derivative. And we want to optimize this one. So in our case, the optimization problem is going to give us an optimal theta for argmin for all theta, which we're looking at, of this function c of theta. So what we've put in square there is a function which will magnify the differences between the solution we want, the exact one, and the ansatz which we have made. So the closer this gets to 0, the happier we will become. That's essentially the iterative process we're going to set up. We will set up a number of epochs or iterations where we will do a back propagation and forward propagation back and forth till this quantity approaches 0. And in the training then, we get new weights and biases. And at the end, we have found a solution, which is the solution to the problem, but now represented by a neural network. Now, everybody here sees that this is a kind of overkill, because if I'm setting up, let's say, a neural network with 5 hidden layers, and each one of them is connected by 100 nodes, so the weights by 100 nodes, I'm going to get tens of thousands of parameters to train. And if you look at the simplicity of the equation which we have here, the solution, clearly, this is an example where using a neural network is perhaps not the smartest approach. However, what you will often see when you apply neural networks to these type of problems is that when the dimensionality of the problem grows, many of these traditional methods, they cannot compete with a neural network. So what are the traditional methods? Now, in the lecture notes, we are going to compare with a famous method, which is called Euler's method. So let me just mention that one, because we are going to use that one as a way to compare the neural network with the standard way of solving differential equations. Now, I said standard Euler's method is not the method of choice, but it's pretty easy to implement. And there are some technicalities which are interesting to study. So let's just remind ourselves about the standard approach for solving differential equations. And as I said many times, I hope you don't get offended if I remind you of Euler's method. And when we come to a two-point boundary value problem, we are going to use a standard linear algebra method, which leads to, in principle, a matrix inversion problem. And I'm just going to mention these so you can see what we are comparing with. So let's do a quick reminder of the standard way. So the standard way means a Taylor expansion. So let's just write this down. And the Taylor expansion then means the following. We are going to look at the expansion either as a function of plus a small step delta t or minus a small step delta t. And this is obviously given by the value at t plus minus delta t. And then I have a derivative dg. We are assuming that this is a function which depends only on t, evaluated at t. We have the higher order derivatives, the second order derivative divided by 2 factorial, and dg, the second derivative at t plus higher order terms with obviously high order derivatives. The other thing which we typically do is we discretize time and we discretize the variable g. So that means that t goes over to a variable t of I, and t of I is given by an initial time, t0, time at t0, plus a very simple recipe. We have I multiplied with delta t, and I goes from 0, 1, 2, up to n, which means again that t of n is actually, or delta t, sorry, not delta t, delta t is actually given by tn minus t0 divided by the number of discretized points, which are often called mesh points or integration points. Now, all the formula, the standard formula, which you will encounter when you study the solution of differential equations, are based on manipulating these Taylor expansions. So if you take the second derivative, you simply add g of t plus delta t plus t minus delta t. And then you can get a formula for the second derivative. If you subtract these two expansions, you can get a formula, a famous formula for the first derivative, etc., etc. If we now just look at the term with g of t plus delta t and truncate that one at the order of delta t, then we get Euler's formula. So let me also remind you of some simple notation here, which you probably have seen many times. This is going over to g of t of I plus delta t. And we often write this as a g of I plus one step. So that means that I can actually rewrite this expansion, which you see here, in terms of these discretized values. Now, in principle, if you guys want to be a little bit picky, we should change symbol of g, because g is not going to be the same g because it's a discretized one. But when we make the step delta t smaller and smaller, the hope is that this g, which we have discretized, approaches the true g value. So if you go in a standard book in mathematics, you will see that G often is, the notation for G is changed to another symbol, simply because G discretized is not necessarily the exact G. But we are just going to keep the same symbol here. So when we then rewrite it, we get that this G of I plus 1 is equal to G of I plus a delta T of G of I derivative. And then we have the higher order terms of delta T squared. And then the standard approximation is to skip the higher order terms. And if we just do G of I plus 1 equal to G of I plus delta T times G of I derivative, then we see that the G of I, the derivative, can then be approximated, and we're putting an equality sign here now, minus G of I, but actually it's not an equality sign, so we should write it as an approximation sign. But normally this is the standard formula which is being used here. So that means that when I set up my solution now, I have a way to continue my iteration. So I would have a G1 at time equal 1 is equal to G0 minus gamma multiplied with G0. So that's the differential equation which I have. G2 is given by G1 minus, G1 minus gamma and G1. And this continues to the final time here, which is then going to be given by Gn minus 1 minus gamma times Gn minus 1. This is the integration which we are going to do in the codes here. And this method has a name after a famous mathematician, right? And I guess somebody already said it here. Does anyone remember the name of the famous mathematician?
Didn't you say it? Didn't you say it?
No, it's actually even before that. It's a German name, but I think he was born in France. Begins with an E. Euler's method. This is just Euler's plain method. Was that what you said? No.
Say it. Said Euler's method earlier.
Okay. Okay. I didn't hear well because I have this earplugs. Sorry for that. Okay. So what I'm going to do now is simply to show you how you can actually run these codes, and with one layer, 2 layers, etc. And the thing which becomes nice for us now is that if we can use automatic differentiation, then we have much more flexibility in actually changing the type of function which we want to calculate the derivative of. So when we are setting up the equations now, we will need to define the trial function. We will need to calculate the derivative of the trial function. And we need the gradient of the cost function. So these are the same ingredients which we have been discussing earlier. Okay? Except that now we are just changing functions. And if we're solving differential equations, it means that we can have many different types of equations we want to solve. So let's take a look at the codes, which you will see in the lecture notes, and go through some of these examples. So in the beginning here, you will see just a repeat of what we said. And this is a typical ansatz which you're going to make, where n now is the function, the neural network. So this is a function of the variable x and the neural network which you are setting up. So that's the architecture of the network. So the minimization process is simply us minimizing this function here. So this is one alternative. You could obviously take the absolute value, but then you would have to calculate the derivative on absolute value. The derivative of this function is actually pretty straightforward because it's a mean squared error lookalike. So we know how to calculate these kind of derivatives. And when you minimize the cost function, you can use gradient descent. this is the machinery which you have set up. If you haven't implemented automatic differentiation yet, this could be the time of doing that if you want to solve differential equations. But still, for some of these simpler cases, you can easily hard code the equations here. So the exponential decay is the case which we're going to go through. I'm going to skip some of these things because this is about actually setting up the neural network. And we have been going through that, so I won't repeat it. I should, by the way, say, there's one thing I forgot to say, actually. So, and I mentioned that last time that we often have summer jobs for people who would like to work on topics related to both research on deep learning, but also on improving lecture notes. And the lectures which you see here were developed by Christine Heim. And most of what you will see here was actually parts of her master thesis. And then she was hired as a summer job doing this. So if you want to, just as I mentioned last time, shoot me an email if you're interested in summer jobs related to deep learning projects. So if we now go and look at the setup of the network. So the first part here, I'm going to go quickly through that because that is essentially the setup of a neural network, which you now have done. We have one hidden layer here. And the final technicalities is that we are going to use the sigmoid as an activation function. The cost function is the function f, which is actually the difference between the right-hand side and the left-hand side squared. So that means that when we now look at the code here, so if we just leave out these terms, so this is what we are going to plug in. So we have the derivative of the trial function, and then we have minus the trial function times this parameter gamma. And this is a function of p here, which is the neural network. And then we use gradient descent as before. And if you look at the code, then you should recognize many of the parameters here. So we have a sigmoid function. We have the setup of the hidden layers and the output layer. We are just reshaping the arrays. And then this is just the setup of the input and the output layers. We have a trial function, which is this one. This is the important part here, which is different from what you have done or what you're doing in project 2. But essentially what you see here is just another way of implementing a neural network. Then we define the right-hand side of the differential equation, which is the trial function times minus gamma. So this is going to be the trial function which we have. This is the right-hand side. And then we define the cost function. And you can see now that in the cost function, we take the element-wise gradient of the neural network with respect to the parameters we have. And then we find the derivative of the trial function with respect to the parameter x, which we have here, which is this one. And then we can define now the function, which is simply the derivative minus the function itself squared. So this is what you see here is my cost function. And then I divide it by the number of samples which I have, and it simply returns a cost function here. So that's pretty straightforward to set up. And if you're using automatic differentiation, the only thing you need to set up is the right-hand side of the differential equation and the ansatz for the function. So the ansatz here is a neural network plus some constants. I hope that doesn't sound too intimidating. It's actually not that difficult to set up with the codes which you have. Now, if you then go through here, what we are doing now is simply to perform the backpropagation. And you can see now that we set up the gradients. We have a parameter lambda. And we are also comparing with the analytical function here. And in this particular case, we are actually doing a kind of overkill. We have only 10 points. And we are doing 10,000 feed forward and backpropagation steps. So this is a kind of overkill. And the whole thing then if we now plot things together, so let me just show you that, you will see now in the beginning, this is the error I make due to my guess. So that's my first iteration, where I now calculate the cost function with a given guess, which is just this parameter G0 plus X times the neural network. And you can see now that in the beginning, it's pretty large. So what you could say then is that, hey, Morten, you could have thought of a better approximation. And probably then you would have spent less iterations on finding the solution. Now, what you see here is an interesting thing here because we get an error which is not that bad. Now, in the next step, so if you look at the results here, it looks decent. There are some deviations, but it looks pretty decent with only 10 points. But let's now be a little bit more ambitious and then add a new hidden layer. And what we're also going to do here, so this is essentially us repeating the same thing, but now having 2 hidden layers. But we're also going to compare this with the numerical solution, which I showed you before with Euler's method. So in that specific case, you will see now that with 2 layers, the starting point is not impressive. It's going to take a little bit more time because I have 2 hidden layers. I have more parameters to train. But then what you will see then is that the final cost, okay, it's actually worse than we had previously. So you could say now that probably with 1 hidden layer and 10 points here, I actually got the result which was a little bit better with just 1 hidden layer. Now, there's one thing I wanted to show you as well. There is another example with population growth, where now the equation is modeled by this one. So the right-hand side changes. We have the GT here. This parameter here is normally called it would be the same as what we had before. That would be corresponding to the initial population. And then there is a dependence on how fast this population dies out. And this is also an equation which has an analytical equation. And here again, we would use automatic differentiation. But what I wanted to show you, if I scroll down a little bit, is actually the comparison we are going to do with Euler's method. Because this is a comparison which in the beginning sounds as if the neural network is doing better than one of the standard equation methods for solving differential equations. But we can, if we just run this, so you can see I know I have 100 iterations. I have 3 layers. I have 100, 50, and 25 hidden nodes. I have a hyperparameter lambda of 10 to the minus 3. And I'm still doing 10 points. And the final time is 1 here. So if I run this, actually here, my ansatz was a little bit better. And you can see now that my max difference between the analytical solution and the numerical solution with neural networks is actually on the order of 10 to the minus 3. But let's now make a comparison with Euler's feed-forward method. It's actually called Euler's feed-forward method. And now we are going to make a comparison where you see now that Euler's method is actually, which is one of the simple implementation, is actually not doing that good compared with my neural network. So my neural network seems to be doing a good job. Now, I want to ask you now, am I trying to oversell the neural network? So I'm doing the calculation with 10 points. So if you look back at what I had with the Euler's method, so with Euler's method, I have a truncation error which goes like delta t squared. So I could obviously make delta t smaller and smaller if I want to. So in this case, I had 10 points. So this is not very favorable for Euler's method with 10 points only. I want you to keep in mind the number here when you now look at the neural network. So if you look at the neural network here, it gives me an error which is roughly 10 to the minus 4 times 10 to the minus 3. Suppose now that I change the number of integration points, so I can solve my problem for 100 points. I can do that for neural network. So I just get 100 function values. So I have more data to train. And now there's an interesting behavior here. So let's just wait a little bit. And sometimes this stuff actually disappears for me when it's running. Okay. And now we see, when we look at the plot here, we see obviously that Euler's method, when I went from 10 to 100 points, is doing much better, which we would expect, because we're having more points between 0 and 1. We are getting a much better approximation error because we have 1 divided by 100 instead of 1 divided by 10. But if you remember back, the number for the neural network, it was 4 times 10 to the minus 3. So what do you notice? What do you see here? If you look at the neural network error, more or less the same, right? Now it's a 3 point something times 10 to the minus 3. And this is one of the things which has not been proven in a rigorous mathematical way, is that neural networks seem to be a method which gives you roughly the same error as you increase the dimensionality of the problem. Now, methods like this kind of finite size methods, or normally we call them finite difference methods, they are very sensitive to the dimensionality. And when you increase the dimensionality of the problem, many of these methods actually start growing huge errors. So is anyone here familiar with Monte Carlo integration? Okay, some of you have seen that. So a Monte Carlo integration has an error which goes like 1 over the square root of the number of samples. That stays constant irrespective of dimensionality of your integral. So if you have a 10-folder, a 10-dimensional integral or 100-dimensional one, the error scales roughly like 1 divided by the square root of the number of samples. Now, if you were to use, let's say, the trapezoidal rule or better methods like Gaussian quadrature, the error there scales in a much more unfavorable way. So what people have noticed from practicing with neural networks is that when you're solving differential equations and you have high dimensional equations, the neural networks tends to beat the standard finite difference methods. And that's a very interesting result, which means that these are methods which in a way take some kind of average for us, and they perform better when the dimensionality increases. So when people are studying turbulence, when they solve the standard Navier-Stokes equation, then by making this delta t smaller and smaller and smaller, and delta x smaller and smaller, increases the dimensionality in terms of points. But what seems to happen then is that the neural network often gives a more stable result than standard solvers. So this is a very active area of research that is applying deep learning methods to the solution of differential equations. So that would be what we might call the natural science type of application to the problems. So obviously these methods have tons of applications, as you probably have seen now. But this is, you probably noticed from my voice here that this is one of my favorite applications. Okay. So after the break, I wanted to end this discussion by introducing another equation and just show you how you can, and we mentioned that last time, how you can solve the Poisson equation. This is a 2-point boundary value problem. In the previous case, we had an initial value problem. You knew the initial value. Now you are fixing the boundaries. And there's a boundary coming up now for me, which says 3 o'clock. So it's not an initial problem. This is actually my boundary constraint here. And we should take a break. And after the break, we wrap up this problem. And then we compare the solution of a 2-point boundary problem And then we are ready to solve a partial differential equation with initial conditions and boundary conditions. And then you have essentially a lot of the machinery which you can use for solving project number 3, or many of the ideas for doing that. Welcome back. And what I want to do now is try to use some 10 minutes, perhaps at most 15, where we look at the slightly more interesting cases. And one of the cases is first a two-point boundary value problem. And this could be Poisson's equation, or it could be a beam which is fastened in both ends, and where you simply force it to be at rest at the two endpoints. And then you have some applied force on the beam, for instance, and then it oscillates up and down. Or it could just be a spring which is fastened in both ends. Or if you want to do Schrödinger's equation, and for those of you who have looked at a particle in the box, this would be the typical example of a particle in a box case. And this is a two-point boundary value problem where you require the solution to be 0 at the endpoints. And this is also called the Dirichlet boundary conditions. So let me just show you quickly the kind of example which we have here. So the differential equation is the one you see there, and those are the boundary conditions. So this is a time-independent problem, and it depends only on the spatial degrees of freedom. The type of problem which you will see solved in the notes here, and let's switch over back to the whiteboard. So this is a simple problem, and if some of you have actually taken a course called Computational Physics 1, is anyone who's been following that course? Okay, this was actually one of the first exercises we normally had, which is this famous equation, Poisson's equation in one dimension. So let's take a look at it. So we have minus g, and this is the second derivative, equal to f of x, where this guy here is a known function. So we know the right-hand side. And in this case, we just have dimensionless units. Everything is made a little bit simpler. These are the domain. This is a domain where x lives. And we have x equal to 0 is equal to x equal to 1. And we have simply this boundary condition here. Now, this is a case which also has an analytical solution. If we now set f of x equal to 3x plus x squared multiplied with the exponential of x. And that gives an analytical solution, and that makes it very useful when we want to compare with the numerics of 1 minus x multiplied with the exponential of x. Now, in our case, what we are going to do now is to be a little bit guided by the insights which we have here, plus the boundary conditions. And one way to make the trial function, in our case, could be the following. So I could now make an ansatz where this g of t, the trial one of x, is given simply by x of 1 minus x times a neural network, and where the parameters theta have to be fit. Now, in my case, that function which we defined, which we wanted to optimize, which is a difference between the right-hand side and the left-hand side, does not contain a first derivative, but it contains a second derivative. And the function g, and this function f of x, and the variable x. So this is a possible way of setting up the trial function, because you see now that when x is equal to 0, then the function is 0. If x is equal to 1, then this ensures that the function is equal to 0. And in this particular case, you didn't need to know anything about this one. But here, I had a hint of what this function looks like. And that means that my neural network is now trying to approximate an exponential. Now, this problem can also be solved numerically by finite difference. And the finite difference scheme, which you have then, let me just mention that because that's plugged into the lecture notes and the code which you have access to. So when we go back a little bit here and you look at the standard equations, like this one, the Taylor expansion, if I add t plus delta t, and then I add t minus delta t, what happens then is that the odd terms cancel. And then I'm left with 2 times this guy plus the second derivative. And that gives, if I truncate at the order of delta t cubed, by simply taking these 2 Taylor expansions, I get the famous expression for the second derivative, which is then given by g of x plus delta x in our case, plus g of x minus delta x, minus 2 times g of x. And this is divided by delta x squared. And that means that when I discretize it, so when my g of x is now going over to g of xi, which we also label as g of I, then I can actually rewrite my differential equation where I have a minus of g of I, second derivative. This is now going to be equal to, and then we have a minus sign, and this is the second derivative, so I should keep this minus sign. So that has a g of I plus 1, plus g of I minus 1, minus 2 g of I, divided by delta x squared. And this has to be equal to f evaluated at x of I, which is the same as f of I. So that's a differential equation. Now, this is a differential equation which you can rewrite as a linear algebra problem. And the linear algebra problem, if you now write it out, you will typically see then when you begin with the boundary values, etc. We know that g of 0 is equal to g of n, which is equal to 0. That's the boundary condition. I can rewrite this as if I now define a matrix A and a vector G. So we can define a vector G now, which only contains the unknown quantities because the borders are known. So I have a G2. So this is the unknown vector containing the solution to the problem, the discretized solutions. I can define a matrix A, which then is a very simple one. It's a 3-diagonal matrix. So it has 2 along the diagonal and minus 1 above and below the diagonals. And then there is this roundest number you can think of here. And if you do that, you can actually rewrite this as a matrix A times a vector G, and that is equal to this constant delta x squared multiplied with f, which is also a vector. Now, what you could say now, okay, I can just invert the matrix and I have the solution. So the reason why I have 2 and minus 1s is very simple. So if you look at the equation here, I get the 2 on the diagonals from this term. There's a minus, minus, plus. And then I have the non-diagonal terms, I plus 1 and I minus 1. And that translates into this one and that one and these terms here. Now, the brute force way would be just to invert the matrix. And then you have the solution G, right? So if you think of this problem, it's just a linear algebra problem, which is equal to the matrix inverse times this vector F multiplied by this constant delta x squared. Now, the matrix you have is a 3-diagonal one. And matrix inversion here is very inefficient because to invert a matrix, if this matrix has dimension n times n, it requires n cubed floating point operations. There is an algorithm which is called Thomas algorithm. And that reduces this to n times 4 floating point operations for this matrix. So you can actually reduce the number of floating point operations down by 2 orders of magnitude. So this is mathematically the easiest way, but from a numerical point of view, it's highly inefficient. But this is something we can do easily, what you have here. This is the way it's implemented in the lecture notes. And then we compare this with a neural network. And the neural network has now an ansatz where the cost function is simply given by the left-hand side minus the right-hand side with this as a trial function. And this is a quantity we have to take the derivative of. So the next type of equation which we have in the lecture notes is the famous diffusion equation, which is a first order derivative in time and a second order derivative in position. Then we will have boundary conditions and initial conditions, because we have derivatives in the x direction. The second derivative requires boundary conditions, 2 boundary conditions. And then I have a first derivative which requires an initial condition. Now, for the diffusion equation, we can actually proceed in very much the same way, but then we would have to plug in here an initial condition. So the diffusion equation which I've set up has the same boundary value problems, which leads to this ansatz for the boundary. But then the diffusion equation is going to have a function h1 of t, which then reflects the initial conditions. So in this particular case, we had no initial conditions because it's only a function in the spatial degrees of freedom. So you will have the same equation when you go to 2 and 3 dimensions, and it's simply called Poisson's if f of x is different from 0, and Laplace if f of x is equal to 0. So these are famous differential equations, which many of you will probably encounter in different thesis projects or courses in numerical differential equations. So in the lecture notes, you will find an example where we solve differential equations like this one, 2-point boundary value problem, or a partial differential equation. And I'm going to show you the solution of the 2-point boundary value problem. And in the lecture notes, you will also find the one for the diffusion equation. And if we get some time, we can actually run that as well. So in this particular case, the problem which we are going to look at is the one which we mentioned. So this is the trial wave function, and we do have an analytical function, which is a lookalike. So in a certain sense, for this specific case, which we have discussed with this right-hand side of the equation, we are going to have a neural network, which is going to try to reproduce an exponential function. And again, when you use orthograph, you can then set up, so this is a neural network with a given number of hidden layers, which you can define. You have the, so this is just a neural network piece, which is actually pretty straightforward. But the thing which is more interesting for us is actually the definition of the cost function. So this is the right hand side of the ordinary differential equation, which is this one. And then we define the cost function. So we have the trial function. We calculate the derivative with respect to x of the trial function. We find the right-hand side. We define the cost function, which is minus the second derivative minus the right-hand side. And this is the function we want to optimize. This is a trial, as you can see here, x times 1 minus x times the deep neural network. Now, again, in this case here, I'm going to do 2 hidden layers. This is very much the way you're going to, or you have been setting up your code. For those of you who have time to do exercises in week 41 and 42, you have this flexibility, simply define this. We define 1,000 iterations. We have a lambda parameter 10 to the minus 3. And then we also compare with the analytical result. And again, what you're going to see now is that, wow, this is pretty big. So my initial guess of a neural network with random parameters is not exactly an exponential. So I get a pretty big result here, right? But then as it moves on, you see now that my final cost is actually pretty good. And the max difference between the solution is rather small. So this is working pretty well in reproducing an exponential. And then we can compare with the numerical scheme, which is the standard one. So this is, as I said, the derivative which we are going to set up, the discretized versions. And then we're going to set up this problem here. So you could actually invert that in a straightforward way, or you could use a smarter algorithm like Thomas' algorithm, which saves a lot of CPU cycles. If you then rerun that and compare it, so this is just, again, the same huge result for the cost function in the beginning, but you see now that it's actually beating my neural network with only 10 points, is actually beating the numerical scheme. But obviously, if I now go back and increase the number of points, my numerical scheme is actually going to do much better. So let's just redo it. So I don't give you the impression that I'm overselling something. So let's just rerun it with 100 points. Then it will take a little bit more time. But now I'm solving the neural network. So the neural network is whether I have 100 integration points or mesh points, as we call them, or not. Doesn't matter for the neural network. It just requires more time. And you see that immediately. But now it's running a little bit longer because I have many more points. I'm solving a slightly more difficult equation. Oops. So maybe I should buy a new laptop here because it's getting pretty slow, actually. And there's also the risk. No, there was no risk that you would listen to one of my horrible jokes because now it's done. Anyway, you can see now that when I increase the number of integration points, if you look back at my neural network, this arrow didn't change that much. But the numerical scheme based on finite difference and Thomas' algorithm now has an arrow which goes like 10 to the minus 5. And if I were to, and actually that numerical scheme runs like this. The neural network is the one which takes time here. So clearly, for these low dimensional problems, a neural network is a kind of overkill, but you see the flexibility here. Because if you look at what we did, if you think a little bit, and let's see if I can trigger some thinking here. If you now look at the program you have for the neural network and the standard finite difference solver, what kind of things do you see for the finite difference solver when I went from the exponential decay to the 2-point boundary value problem? What happened then? So let me give you a kind of hint. So when I did the 2-point boundary problem, I have this equation. So what is the main difference between here and what I did with the exponential decay? The answer is pretty obvious. I have to write a totally new algorithm. I have to implement a new scheme. And that requires time. With a neural network, the only thing I did was to change my ansatz and the trial function. And then with automatic differentiation, I could rerun my neural network. So in a certain sense, the neural network now, even if I use a pretty brute force ansatz, is almost agnostic to the type of problem. So if you have developed such a code, you can then apply it to many, many different types of equations. If I, on the other hand, now want to solve a diffusion equation, I have to implement a totally different numerical solver. Yeah. Because you can play around with a different number of nodes, different number of hidden layers, activation function, that's something you have encoded. So you are flexible, like the kind of network you guys have been writing on, you can then decide how many hidden layers you want, what type of activation function. That's just the architecture, the model, which is plugging in. But then the only thing you need to change, if you use automatic differentiation, is the type of trial wave function, where you have to plug in the insights you have about the problem. And then you have to set up the derivative. And then if you run with the same type of cost function, which is the difference between the left-hand side and right-hand side squared, you don't need to change that part. So the only thing you do then is actually to change the trial wave function. Whereas when we now in the slides here, and I'm not going to cover that one now, I leave that to you guys to take a look at. But if I'm going to solve the differential equation, then I will still have something similar like this, but now you have more variables. And I'm still going to optimize something like this, but now I have to be careful because I need more derivatives. But that's the only thing which changes. So what changes is obviously the boundary conditions, the initial conditions you have, and the type of derivatives. But with automatic differentiation, you can easily set up these derivatives without too much pain. And for the diffusion equation, this means that this is the equation you want to solve. And now I've just taken away all physical constants. And then these could be the boundary conditions, which you have here. And this could be the initial condition, which is given by some function. And the only thing you need to do then, when you're setting up the problem, is actually to find the correct form for the guess for the trial wave function, which you're going to set up. And I think I put it up here. When you're setting it up, this is a function which would contain the initial conditions. This is the one now which contains those boundary conditions. But you see now that I want to have at t equals 0, I multiply with t here. So this is just an ansatz for the trial wave function. And you see then that this function, which now fulfills the boundary conditions you have with this u of x equals sine pi times x, could be something like this. So with this kind of guidance, you're then ready to reuse your differential equation solver. But it's going to take more time now because you have 2 dimensions, and that obviously normally requires much more time. So the strength of these methods, which we see from numerical results, is normally when you go to higher dimensions, because then that is where they normally beat methods like the finite difference ones you saw previously for the Poisson equation. Okay, I'm going to stop here with differential equations. This is going to be one of the possible tracks in project number 3. And I know that there is always many of you who've been studying numerical differential equations with other methods. That means that you can bake in those results into project number 3. So if you've taken a course on solution of partial differential equations with finite difference and finite element, these are things you can bring in and compare with what your neural network code gives. So that has been a very popular path in project 3, and we're going to keep that one as an option. Any questions for this? Okay, so what we are going to do now is to change topic, and we are going to discuss in the rest of the semester convolutional neural networks and recurrent neural networks and autoencoders. And now we are entering the topic of convolutional neural networks. And in the rest of the lectures, I wanted first to give you motivation and then demystify what these are about. And then next week, we're going to look at some of the mathematical details about CNNs. So I'm going to skip some of these things. I'm not going to run them because they also take a lot of time. And then you could easily have risk to run into my lame jokes. So there's also a set of references here if you're interested in looking at that. So they were actually developed during the last decade of the previous century. But nowadays, they're actually the backbone of classification of images. Is really the method of choice. And the big difference is that they are normally applied to inputs as the images, which allows you to encode certain properties into the architectures. Then these then make the forward function more efficient to implement and also reduces the amount of parameters in the network. So one way to think of a CNN compared with a neural network is that a neural network normally requires that you have a dense matrix of all the weights plus the biases. And that means that if you have thousands and thousands of nodes, you end up with hundreds of thousands and millions of parameters. So a CNN is meant as a way to reduce the dimensionality. So let's see how this is happening. So as I said, there are things like, I just want to give you some words first. So we normally call neural networks as affine transformation. That's a vector is received as input and is multiplied with a matrix of so-called weights. And then we have a series of matrix vector applications. And we don't do any reduction of the dimensionality. So these transformations are made through the network. And at the end, you come out with a prescribed final dimensionality of your output. The CNN has been used on many topics. I have several of the students which I have guided have ended up using CNNs in actual work, whether this is research in, let's say, the medical sectors. When you look at scans, this is an extremely interesting area of research to develop proper ways to recognize different types of illness. It can be different types of tumor, etc., etc. So typically scans, you would often have tons of images with many pixels, and then you want to reduce the dimensionality of the problem and be sure that you can recognize this or that type of illness or whatever kind of things you're actually looking after. So we have one here who's doing a project on images of mouse, and where they're actually looking at cardiac disease in mice. And then you have lots of slices of how the heart moves in the breast of a mouse, and then over time, and then you can analyze whether this is a mouse which will develop a cardiac disease or not. And that's a typical example on how you would use CNNs. So for many of you who, let's say, you are into classification problems in your master thesis, this would be a typical extension of project number 2 into project number 3, where you then compare a neural network, which doesn't do any dimensionality reduction, with a CNN, which does that for you. And CNNs have been trained, actually, there are many deep networks. There is a very famous data set, which is called ImageNet, which contains millions of images. There's another one which is called AlexNet, after a guy whose first name was Alex. And these are popular data sets which have been used in training models for image recognition. So these models can contain then images of cars, of cats, dogs, whatever. So this is the design of the filters which reduce the dimensionality is an art by itself. And one of the things which we have to face, if you now look at this example here, if you think of a neural network, one of the reasons why CNN have become so popular is that the NNNs, the neural network, doesn't scale well to full images. So if you look at this image here, and this is pretty common, is that you have 3 color channels, and you have an image which is 32 pixels wide and 32 pixels high. So that means that if you have a single fully connected neuron in a first hidden layer, then what you would have would be 32 times 32 times 3, 3072 weights. That's only if you have one. And this amount seems manageable, but if you are doing an image of 200 times 200, you would have 120,000 weights. So this quickly escalates. And one of the problems with a standard neural network is simply that it's actually not scaling well enough with the dimensionality of an image. So a CNN, and we are going to break this down a little bit more when we come to the whiteboard after we've gone through some of the slides, is typically you having an image. This can then be scaled down, but you can make replicas of the image. That's pretty common. And then you can have further replicas, and then at the end, you would flatten everything out. So I have another examples of dimensionalities here. If you're dealing with signal processing, and this is also something you would also have in imaging, what you design is so-called filters if you deal with signal processing. So if you have a vector of length 10 to the 6, if you then construct a neural network with only one hidden layer with 10 to the 4th nodes, that means that you will have 10 to the 10th weights to be determined, together with 10 to the 4th biases. And if you have an output layer, which is meant to train whether the sound sequence represents a human voice or something else, so you have a binary case, it means that you only have one output node, true, false. But since the output connects to 10 to the 4th nodes, then this is the total number of parameters you would need to train. So something on the order of 10 to the 10th or 10 billion parameters. So that clearly tells you that in one way or the other one, we should think of methods to reduce the dimensionality of the problem. So one of the things which I want to do before we move on into more the mathematics is to give you the kind of structure of a standard CNN. So let's just switch back to the whiteboard here. And what I'm going to show you now by an image is the standard layout. So there is an input layer, and then there is something which we call a convolutional layer, which is a filter which then reduces dimensionality of the problem. And then there is a so-called ReLO layer, where you simply have a thresholding, which then leaves the size of the image unchanged. And then there is a pooling layer, which is a further way to reduce the dimensionality, where you typically can keep only the max values coming from this ReLO layer. And then when you've reduced the dimensionality here, suppose now it's down from 32 times 32, which was your initial, times 12, then you're down to a downscaled image. Then there is a fully connected layer where you simply flatten out the results. But let's now try to look at the basics here. So this is often how you would see it. So you have a CNN architecture, which now contains a so-called convolution stage, where you now do a filter. So the filter has dimension 5 times 5. And then you make 32 copies. So one thing which is often done then is that you, by this kind of filters, which applies to the original image, which is a 20, in this case, 28 times 28. So this could be the MNIST data set. I now have a filter which reduces the dimensionality to 20 times 20, but I make 32 copies. Then through this pooling layer, I reduce the dimensionality further so that I make now 32 copies, but they have been filtered down to 14 times 14. I now have a new convolutional layer where I now reduce everything for pooling to 7 times 7. So the hope then is that this filter keeps track of some essential parts of a certain part of the figure. And then by making all these replicas, you have more data to train on, but at the same time, you have scaled it down. And Then you flatten it out like a long vector, and then you have 10 outputs. So this is the MNIST data set, and then you're actually looking after only the 10 images which you want to train on. So you start with a series of images with 28 times 28, and then you make these replicas more and more, and you have several replicas of the image, and then you feed that through a feed-forward part. So you will have now parameters in the convolutional stage. There will be a 5x5 filter, which that, yeah. Yeah. So the filter kernel is actually the same name. So these are just synonymous. So you can think of you being able to find important traits of an image, which you filter out, and then you place yourself different places in the image, and then you make copies of it, so that hopefully then you have the full image again, but through many copies. And the whole idea then is to reduce the dimensionality. So at the end, when you have done this process, so here you would actually have two convolutional stages. So there is one, a filter here, and then you have this pooling, which is a way to reduce the dimensionality. We're coming back to what that means. So this is one convolutional stage. Here you have 25 parameters. You have a new set of parameters, so in the convolutional stage, which are then trained by backpropagation. So backpropagation is the basic algorithm. Then, when you flatten it out, this FC is just a standard feed-forward neural network, which has been, where the data has been flattened out. And then you train this one by standard backpropagation. So you would have parameters in here, trained by backpropagation. You would have parameters here, trained by backpropagation. And you would have parameters here in this filter or kernel, trained by backpropagation. That's the kind of bird's view on a convolutional neural network. So what comes into addition to what you've done till now is actually this filtering down of the image. And this is what we are going to cover now, what this actually means mathematically, and what this pooling actually means. And then there is something which, some other parameters, which are called padding and stride, which we have to get a little bit familiar with, so that we can set up the parameters needed for a convolutional neural network. Now, to write your own code for a convolutional neural network is easily a semester-long project. So that's why we are going to use PyTorch and or TensorFlow, if you want to, for the final project, when we are going to use CNNs or RNNs. Because as you can see here, at the heart of everything, deep in the network, there is a feed-forward neural network where we flatten out everything and do the standard backpropagation. So in all of these methods, whether you're doing reinforcement learning, transformers, et cetera, there is at the heart, there is a feed-forward neural network part. So having coded that one gives you the insights about the essentials. Now, what comes in addition are actually all these different properties, like the convolutional part, which implies more parameters, but is used to reduce the dimensionality of the problem. So when we come to recurrent neural networks, they can also contain inside in the black box, either a feed-forward neural network, or it could even be a set of convolutional neural networks. So that's actually pretty common. So if you're doing time series of data with images, then at every time step, you could have a black box with convolutional neural networks. Okay, so let's try to look at some of the key ideas here, and then look at the switch to the whiteboard. So let's try to do that. Oops, nope. So let's get started with CNNs. and then take the overarching view here. Overarching view. So what we typically have, and in this case, we have only one convolutional layer. So we would have the standard input layer as before. And this could be our MNIST data set. Then there is a new layer here, and we normally call this for the convolution part. And in the convolution part, there are typically, if we now just put in arrows here, in the convolution part, there is one part which we call the mathematical convolutional stage. So let's just mark that one. So I call this convolution part because it includes the convolution itself, which is the filtering of the data. So this is the mathematical convolution. So this is often called the filter or the kernel. So this is where we now can reduce the dimensionality and make replicas of the images. Then from that one, we feed into what is normally called a ReLU function. That's pretty common to have a ReLU layer. So that doesn't have any trainable parameters. So here we would train these ones, the convolutional layer, trained by back propagation. Backprop. When we look at the next stage, this stage here, this is just a ReLU function with no trainable parameters. And this is fed into what's called a pooling layer. So we're going to write this pooling. And this is also a function which is set by us because we define the pooling layer and how we are going to extract information. So this will also reduce the dimensionality of the problem, but there are no trainable parameters. So this is set by you as part of the architecture of the network. And typically the way you do the pooling becomes a parameter which you would play around with. So when you do the training, you fix it, and then you can do a new numerical experiment where you fix it, and so on and so on. Now, this produces a downscaled result. And since I'm not very good at making images, so the downscaled result here goes into a feed-forward neural network. So I just write it FFN NN. And that is where you do the training by back propagation. So again, we can put an arrow here. So the parameters here are trained by back propagation. This feeds into the cost function and the output layer. So we have a cost function here, which then gets in the target values Y. So then we would typically start calculating the derivatives here. We go back to the feed-forward neural network, back propagate. Then we would just go through the pooling layer and into the filter layer and train the parameters there by back propagation. And then we have trained new parameters. We do a new convolution down to the feed-forward neural network, out to the output, and then back and forth again. So the difference now is that the convolutional part is something you can view as a way to scale down the size of the image. And this is the essential part of the CNN here. So what we are going to look at next time, I see my time is running out here. I'm always too slow. But next time, I want to go through the mathematics and how we define different parameters which are used to scale down the images. And then at the end of the next week, we are going to see how we can write a code for a CNN using PyTorch or TensorFlow. And in the book by Rashka, in chapter 14, you will actually find a nice example in using PyTorch, which I also have used in the codes you will find in the lecture notes. So this week I was hoping to go through more mathematics, but I will have to postpone that till next week. I'm always too slow. Okay, guys. It's always a pleasure to see you guys. Take care and see you at the lab here.